we will go from current slide, and I'll turn on the projector. Okay. But we do have a few announcements first. First, this came out awfully late, but it's out now, so please note. Are any of you taking a first mini-term course? None. Smart people. Okay. If you know of anyone who's taking a first mini-term course, the student course evaluations, the surveys are now been opened with 2 days left in the term, in the first mini-term. So that's, pass that along to anyone you know that's in a first mini-term course. Which also means that we are approaching midterm. That will be next week sometime. And shortly after midterm, they usually ask for midterm progress reports. This class is doing exceptionally well with that, with just a couple of exceptions. I don't have a score for 2 people, okay? And it can be either the research paper or the first test. But as soon as I can get those 2 first tests in, then I can return them to everybody else. But one of those is out with the flu. So he's probably working on it as we speak, I'm sure. Okay, no, I'm not sure of that at all. Okay, now that's college-wide. Let's talk a little bit about my schedule. I think I mentioned this last time. Last Friday I had to be out of town. We left at 6 and got back about 3:30, earlier than I had feared we would be. But it was still a 9.5-hour day for my 4-hour workday on Friday. So I asked my boss if I could be off this Friday as well, because I had already worked so many hours last Friday. And I really regret that we have to be out of town, but we do. So I will not be on the Birmingham West campus this Friday either. Okay. Hopefully next Friday I'll be back almost regular hours. I know I have a doctor's appointment next Friday, but I asked them to schedule it for me in the afternoon. I just don't recall what time they said they were scheduling it. So hopefully that won't interfere. If it's too early in the afternoon, I may have to leave campus a little early to get there, but otherwise I should be there. All right, so that's, I'll take that back. We do have professional meetings that Friday. I haven't registered for it yet, but I saw that they were begging people to register, so I've got to find out if I need to register for that. So that may be 3 Fridays in a row I'll be gone, but we'll find that out later. Okay, next. This won't affect y'all any, but it will affect my presence on campus to some extent. Next Tuesday, I have a doctor's appointment that's at 10:40, but I have to leave. I have to be at there for blood work at 9:40, so I'll be leaving campus at 9 o'clock. So I'll be in my office next Tuesday from 8 to 8:30 as normal. But then normally I'm in class after that, so I'll be in class for the first 30 minutes, and then we'll be gone until I'm back from the appointment. Then I have my, that's the last day for my first mini-term class, and it looks like we may actually be going on a field trip that day, so that may mess up those hours as well, but I'll be back in time for that. So it shouldn't mess up my office hours much. That Tuesday, Thursday, I have a office hours from 12:45 until 1:15. Hopefully I'll be back for those. Okay, that's Tuesday. Thursday, however, I'm gone all day. We've got meetings in Tuscaloosa. It's retirement meetings. They want you to go to these, so you make sure you get everything done properly, so there's no screw-ups when you go to retire. It helps them, it helps me, so they want you to go to these meetings. So I signed up for the one in Tuscaloosa, because they don't offer any in the biggest city in the state, Birmingham, nor do they offer any in Bessemer. Tuscaloosa was the closest to here, so I requested Tuscaloosa. Then they assign the days, and they assigned me next Tuesday. So I'll be gone all day. It's an all-day meeting. So none of my office hours I'll be here. I'll be probably on the road to Tuscaloosa at 8 o'clock, and I think the meeting starts at 9, so I'll be gone. And then I think I may be back here late in the day, but I can't guarantee that either. Okay, that's Thursday of next week. And like I said, Friday I do have another medical appointment, dermatology appointment in the afternoon, so hopefully that won't mess with office hours too much. Unless, of course, I go to the meetings. I don't think I can because of my appointment, so those are out of the question. Okay. Do you have any questions? Okay. We left off last time in Chapter 3, Differentiation. 3.4 is the chain rule, which is a very powerful rule you'll be using forever. Okay? It is very much, in fact, it'll get so you don't even think you're using it because it just comes so second nature. We're going to move now. We've been looking at regular functions, power functions, other things like this. Oh, all of a sudden light comes today. Huh? Okay. So Kyle's here. We go. And just the only thing of note of the employees, are you taking any mini-term courses this term? Yeah. Okay. If you know of anyone who is, the student course evaluations have finally opened for those with 2 days left. Okay, so they really take it to the wire. So we looked at chain rule with power functions, with polynomial functions, with all our regular kind of functions. Now we're going to look at some of the transcendental functions in the chain rule. Can anyone name some transcendental functions? For those of you who have the older books, this is in your chapter 5. You'll find almost the same stuff there. I just can't tell you what page number and stuff like that will be. All right. I haven't looked it up to see. What are transcendental functions? Name one or two for me. Sine and cosine, tangent, cotangent, all those trig functions are transcendental. Any others? Sleeping, they say you're sawing. No. Logs, okay, log functions are transcendental functions, and the inverse of that is? Exponential functions are transcendental functions. Those are most of the ones we will be fiddling with now, and here's generally the rules for them. The chain rule versions of the derivatives of the 6 trigonometric functions and the natural exponential functions. Okay? d by dx, now this is your independent variable now is x, but you're taking this of sine u. The implication here is u is some function of x. Okay? And if that's the case, d by dx of sine u would be, take the outer function first, derivative of sine is cosine, and then you take chain rule derivative of u prime. Okay? What's d by dx of cosine u? Negative sine u, exactly, but then you do u prime, the chain rule. Okay? Take the derivative of the outer. It doesn't matter which order you do them, but you just need to do them both. Derivative of the outer, then the derivative of the inner. Okay? What's derivative of tangent u? Secant squared u du, because your independent variable is x, you have to take the next derivative, the derivative of u with respect to x. How about cotangent? d by dx of cotangent u. Negative cosecant u, secant squared u, times du, u prime, exactly. What's the derivative of secant u? d by dx of secant u. secant u, tangent u, du, u prime, exactly. Cosecant u, negative cosecant u, cotangent u, u prime, exactly. How about d by dx of e to the u? Well, real hard. E to the u, u prime, du. Now, they left off the log. What were they thinking? Okay? Or were they thinking? Let's do the log. I don't know why they didn't here, but let's go on and do it. Do y'all remember what the derivative of the log is? Did we do that? I think we did. Anyone remember? Whoops. My pen is not working. Or it did work incorrectly. Okay. All right. D by dx of log u. Anyone remember what that was, or if you knew it? I don't know. Have we done it? It seems like we have. I'm teaching so many different classes I can't keep straight which it is. If we haven't done it, here's what it is. 1 over u times u prime. Derivative of log is 1 over the argument. Okay? Now you might say, wait, that, wouldn't that have been a power rule type thing? Well, not really. Because, well, I won't get into that, but if you had reduced that exponent or increased that exponent by 1, you'd have u to the 0. And then you would need a 1 over 0 in front. And that will not work. So that is it for log u. Surprised they didn't have it here. Okay? But in case we haven't done it, there it is. All right. Any questions on those? Let's do example 10. And I hate it. Okay. Find the derivative of y is equal to sine 2x. What would that be? Help me. Say again? Cosine of 2x. There's the first part. And what is the derivative of 2x? 2, yes, okay. So you can just write it as 2 times the cosine 2x. And this is an example of why some people like to do the derivative of the inner first, because it winds up coming in front, okay? And then do the derivative of the outer function second. And it doesn't matter because they're multiplied together. Multiplication is commutative. It really doesn't matter. But you can do it this way too. Why do you think you might not want to leave the 2 on that side of it? Someone might misread your handwriting and think this is cosine of 2x times 2, which would be 4x. Or if you're really sloppy and it looked like that was an exponent, that would be 2x squared. Really a good idea to put that 2 in front so there's no ambiguity. 2 times the cosine of 2x. You don't have to write it that way. So that's usually a lot clearer for whatever you might do next. Any questions on that? Okay? How about this one? What is the, if y is equal to cosine x minus 1, what's y prime? Negative sine of x minus 1. What's the derivative of x minus 1? Okay. Derivative of x is 1. Derivative of 1 is, or negative 1 is 0. So that doesn't contribute a thing except the number 1. And of course we don't even write number 1 down. So that, the chain rule part of this gives you nothing new. Up here it gave you something new. Here it didn't. It just was 1. So that, I wouldn't have encountered that as chain rule problem. Okay? But they did. How about this one? Y is equal to e to the 3x. What's y prime? A little louder. E to the 3x times derivative of 3x, which is 3, so that'd be 3e to the 3x. And again, this is why a lot of people will do the inner function first. Derivative of that is 3, and then derivative of e to the 3x is equal to 3x. Okay? Doesn't matter the order you do them, but it's a good idea to put that 3 in front. If you had left it behind, that'd be e to the 3x 3. That just looks weird, okay? So someone may misinterpret what that means. All right. That was example 10. Any questions on those? Does it make sense? Anything ambiguous? Okay. Now, they're skipping examples 11, 12. Oh, there's where they're going to get the derivative of the natural logarithm function. So I jumped the gun. Sorry about that. There'll be no extra charge for getting it to you soon. Okay? Let's go back and do example 11. All right? Strange little topic here. Here is the... They don't tell you what to do with them, but you're supposed to take derivatives. A good idea, right? Y is equal to cosine 3x squared. Okay? If I told you that and said, what's y prime, you tell me what you think it is. In whichever order or way you want to do it. Okay, certainly going to have a negative sign of, what'd you say? 3x squared, that's good. And what else do you have? Chain rule. Anybody? Derivative of 3x squared, which is 6x. 6s. Oh, no, 6x. Okay, something like that. Okay? Now, again, that looks a little bizarre, so I would write this as minus 6x times the sine of 3x squared. Okay? See how the book did? Oh, good for them. They got it right. Does that make sense? Okay? Let's do the B part. Y is equal to, oh, this is silly, cosine of 3 times x squared. You know what? In all my times of doing mathematics, I've never run into that before. Okay? I've never seen anyone, well, never. Okay, what would you do with that? Any ideas? We want to find y prime. And remember good old Aunt Sally, or Sue, or whatever her name was? What did she have to do with it? She did something. Just said, please excuse her, right? Okay, how did that go? Second? Parentheses first. Okay? That's, what is cosine 3? I don't know, but it's a number. 3, obviously, if it doesn't have a degree symbol, that's radians, okay? And cosine of any number of radians is just a number. So this is a coefficient, and that's the power. So what's your derivative? 2 times cosine 3, and that's your coefficient. And you better put something in parentheses, either the whole thing or at least that part, and then do an x there. Okay? If you didn't put the parentheses here, that would look like cosine 3x. That's not what you got here. So you need the parentheses just for clarity. Okay? That should be your answer. How did they write it? They chose another way, which is perfectly fine. They chose to write it as 2x times the cosine of 3. And that's fine too. It just looks weird, but it is perfectly fine. Okay? Now, aren't you glad we're not using webasine? They would say, that's the only correct answer, whereas this is just as correct, okay? Just as fine. But there's no preference whatsoever. This one has extra. I guess if you were a typesetter, you would like to eliminate as many items as possible, so you eliminated the two parentheses, the right and left parentheses. Okay, that was worth it. How about this one? Y is equal to cosine of 3x squared. Now, what would be perhaps the first thing you would do to that? You don't have to, but what would be, well, how would you approach it? I'll let you handle it however you want to. What would you do for that? That's what I would do. I would rewrite this as cosine of 9x squared. Now, and you can put it in parentheses or not, it doesn't matter, do the y prime of that. Of this one. And what would that give you? Negative sine of 9x squared what left times 18x, which I would probably, and I think they would too, rearrange to be minus 18x sine 9x squared. Okay? Let me make sure. Negative 19x sine x squared. 9x squared. Perfect. Now, I do want to, not that, this is how I would do the problem too, by the way, okay? But I want to show you something else. You can use the chain rule repeatedly. This one, the way it's written here, you could do that, okay? The outer function is cosine, so I'm doing it, this one, this way. So that's going to be minus sine of 3x squared, okay, just like they did. Then the derivative of the inner part. But there's two inner parts. Do the outermost inner part, which would be, I'm going to put it in parentheses or bracket here, 2 times 3x, right? Exponent times that, okay? Then, that's times again the derivative of the inner part, which is 3, okay? And then if you combine all those things together, you start with the minus sign, that's still there, okay? And then you have 2 times 3, which would be 18, x sine, and then I would well, if you wanted to leave it the way it was, you could, 3x squared, which is the same thing as what we had, okay? But they did it like we did. Go on and simplify this first and then take it through. But I didn't want to do this because you see you have an outer function, cosine, a intermediate function, the squaring function, and then the innermost function, the multiplied function, multiplying by 3. So you can do the chain rule multiple times. And keep going in and in and in. Much easier to go on and multiply the thing out to begin with, like they did. All right, let's do D. Y is equal to cosine squared x. Whoa. Okay. Now, anyone want to make a stab at what that one would be? Anybody? Yes. A little louder, I'm sorry. 2 times cosine x. You're right. The outermost function here is the squaring function. You know how to square something. 2 times this, drop the exponent by 1. So that would be 2 times cosine x. Are you through? Please say no. Okay, no. What's next? Say again? That was the outside function. The inside function is cosine. You need to take the root of that. What's that? Times negative sine x. Okay? And then when you rearrange this, it'll be negative 2 cosine x sine x. And that's a perfectly good answer. But because I know all of you remember so well your trig identities, right? Yes, I know who you had for trig, some of you. Okay. One of you anyway. Okay. Christian? Okay. Anyone recognize what that is? I can't get my pen right. I shouldn't do this, but there indeed is what it is. Okay? And let's see if I can find that for you. The front inside, now this is at least the new books. I think probably the old book is like this too. Front inside cover. If I can get the page to pick up, my thumb is all thumbs. Okay? Double angle formulas on the top thing on the right-hand column under the unit circle there. Sine of 2u is 2 sine u cosine u. That's 2 sine x cosine x. That's the sine of 2x. You had a minus in front, so that's that. I bet you they didn't take it that far. You don't have to. This answer is perfectly good, perfectly fine. You could have written sine in front of cosine if you prefer it. That's fine too. They did not. And if you had and were doing Webasine, it would say it's wrong, okay? And where it doesn't really matter which one you put in what order. And they probably say that was wrong too, and that would be perfectly correct as well. But that's why I don't use Webasine, okay? But you have it out there for you. You can use it to your heart's content. I just don't require it, okay? Now, how about this last one? Y is equal to the square root of cosine x. You tell me what you would do first. If you've been around me long enough, I think you know what I would do first. What's that? I hear movement. Yeah. Say that one more time. Okay. Are you saying rewrite? I would agree with you. Now, how do you rewrite it? I heard cosine. Someone help me. Cosine to what power? You may have said it, I just don't hear well. Say again? No, that would be cosine squared. That was what this one was. I don't think cosine squared is the same as square root of cosine. If it were, then let's just say I owe you, no. Yeah, you owe me the square root of $4, but you say, well, I'm just going to pay you $4 squared. I would take it, okay, in a flash, okay, because one is 2 and the other is 16. I'll take the 16 if you owe me 2, and we'll be happy. We'll call it even, okay. I don't think they're the same. What would be the exponent for this? A little louder? 1/2. Perfect, perfect, perfect. Cosine to the 1/2 of x. Okay? Now, how would we do the y prime of that one? That is now what kind of function? Lots of kinds of function. But the outside is your power rule. How does that go? Oh boy. 1/2, there's a good start. Cosine to the, second, negative 1/2 x. And let's see, are we done? No, we're not. Because we still have an inner function to go. And what would the inner function be? The outer function was your power function. The inner function is? Okay, and what's the derivative of cosine you said? Negative sign. So I'm going to put the minus sign here and the sign here. And it's not sine to the negative or the 1/2 or anything else. It's sine because you're doing the derivative of the inner function, which is cosine. Okay? Now, how you rewrite this, that's your choice. Here's one, I think, fairly concise way to do it. The 2 is in a denominator. The negative 1/2 moves that to a denominator. The minus sign can be out front. And the numerator, only numerator left is a 1 and a sign. So I'm going to put a sine x up top. I'm going to put 2 cosine. And you could put the square root of cosine x if you wanted to, or put it to the 1/2. Which you prefer? Square root or 1/2? I don't care. Cosine to the 1/2 power x. Okay. I don't know if that, guess what? They did it the other way. They did negative sine x over 2 square root of cosine x. Same answer, negative sine x over 2 times the square root of cosine x. Okay? Those are exactly the same answer. However, Webersine would have said, that one's right and that one's wrong. It wouldn't be wrong. Okay? That's why I don't use Webersine. But you're welcome to use it to your heart's content. Okay. Now, what I had already talked about, how you can use the same chain rule several times, we're going to do in example 12. They just have one of those. Any questions on the 11 before we move on? Now, what the whole point of the first part of this was this, and this all have the same digits in them, okay? It's just where you put the parentheses. This makes cosine 3 just a constant. This makes your argument a composite function, 3x squared, okay? Whereas this is 3x squared. They sound the same, but they are different because of where the parentheses are. All right, ready for 12? Okay. I will erase what I got unless someone screams. Oh, anyone still writing? Got it? Okay. You need it any longer, Joanne? Okay. All right. Example 12. This is sort of one like I pointed out to you before, a little more complicated perhaps. F of t, they go into a new variable is one thing, is equal to sine cubed of 4t. they don't even put parentheses. I kind of like that, but they don't, and it's fine not to. Okay? And what we're looking for, of course, is f prime of t, the derivative. Where would you begin? Anybody? Anybody?
Put the x bar on the outside.
The what?
Put the x bar on the outside.
Okay, in other words, you're starting with the outermost function, which is the cubing function. Okay? And how you handle that is you do 3. So go on. Sine to the second. Is that what you said? Please say yes. Okay. All right. Of 4t, right? Okay. You've done the first step, the outermost function. What's your next step? Anybody? Of what? Which what? Yeah, okay. Take the derivative of sine next. And what's the derivative of sine? Cosine of 4t. Okay, you're right. You were saying it right. So I'm going to put that in parentheses. I don't need to, but I'm going to. And then we got another inner function. What's it? Four t. What's the derivative of 4t? 4. Got it. All right, so let's combine what we got here. It's kind of a mess. But 4 times 3 is 12. And it doesn't matter the order you do the rest of it. I'm going to write it just as it shows up here. Sine squared 4t times cosine 4t. Now, if you're really a glutton for pickiness, you could take one of these sine of 4t out with the cosine of 4t and a 2 out of this and make that a sine of 8t times a sine of 4t times 6. But let's not do that and say we did. Okay. Yeah, they leave it just like this. 12 times sine squared 4t times cosine 4t. They even left it in the same order I did. Does that make sense? Yeah or nay? Okay. So that's example 12. Let's move on, unless there's questions. Any questions? Let's move on to derivative of the natural logarithmic function. So I did jump the gun on you. I had thought we had done it. We hadn't. Here it is. We're going to do it now. But you already know it now, don't you? So we could almost skip this, right? The derivatives of algebraic functions have been algebraic, and derivatives of transcendental functions have been transcendental up until now. The following theorem looks at an unusual situation in which the derivative of a transcendental function turns into being algebraic. Okay? Never thought of it that way, but it is. Specifically, the derivative of the natural logarithm function of x, log x, natural log of x, is 1 over x. I didn't spell that out clearly, but that's what we got. So here's your theorem 313. Let u be a differentiable function of x. Then d by dx of log x, and this is what I said, is simply 1 over x. With one huge caveat. Okay? I don't know if you remember this or not. What can x never be? You've taken the log of it. It can't be 0. You're absolutely right. And it can't be negative. Okay? So in other words, x has to be greater than 0. Can't be 0, can't be negative, so it's got to be positive. Not including 0 is positive. Okay? Now, if you put a u in there rather than a x, what would that be? You tell me. 1 over u is the first part. Yeah, du dx or u prime. Now that produces an interesting situation, because this you could write as u prime then over u. And that's pretty interesting. And again, x has to be greater than 0. Can't be 0, can't be negative. Always has to be greater than 0. Okay. The x, okay? I would say the u also, okay? Because they haven't even put the x in here anywhere. So I'm not even sure this is a true statement. I think that's supposed to be u greater than 0. X could be something else. If u was x squared, or x plus 1 squared, you wouldn't have a problem in the world. Okay? Let's see if they wrote it in the book correctly. No, they said x greater than 0. I kind of disagree with them. I think it should have been.
You're saying it's supposed to be u?
Oh, I thought you were leaving me a card. I thought I won. Okay. Okay. I think that should be u greater than 0. I don't see any reason to say x has to be greater than 0. I think it's u greater than 0. Okay. Now, in the book, they go through a little proof, and it's a pretty good little proof because it uses the property of the fact that natural log is the inverse of the exponential function, and when you go through and do that, you'll see it gets to be exactly that. So, let's do example 13. Now, one special thing about example 13 is you can go to larsoncalculus.com for an interactive version of this type of example, but who needs it? Okay? We can do it. What is the derivative of log of 2x? Say that one more time. Did I hear 1 over u? What's your u in this case? 2x. 1 over 2x. Oh, they're saying u prime over u. Oh, you said u prime over u. I'm sorry. I don't hear well. That's exactly correct. U prime over u. Okay. Well, what's your u prime? 2 over x. You got it. I mean, yeah. 2 over 2x, which is 1 over x. Which is bizarre. That was what, if that had just been an x there, it would have been the same thing. Because your u prime, your u is 2x, u prime would be 2, 1 over 2x is your outer function. The derivative of that would be 1 over 2x. The 2 divide out, and you're left with 1 over x. Okay? Which would be the same as if it had been the derivative of log x. Interesting. Okay, let's do the next one. Oh, how about this one? D by dx of log of x squared plus 1. Anybody? Okay, you got 2x as your numerator and over x squared plus 1 as your denominator. Perfect. Okay, u prime over u. Now, up here they didn't say it, and you really should say it. They should have put in parentheses after that, x has to be greater than 0 for this one. It has to be greater than 0 here, it has to be greater than 0 here. How about here? What is your domain here? Does x have to be greater than 0 here? No. U has to be greater than 0. That's why I said I didn't agree with them saying x has to be greater than 0. U has to be greater than 0. But guess what, team? X squared plus 1 is always, and the real number system is always greater than 0, right? Because if x were negative, you square it, it's positive, add 1 to it, and it's even more positive. But even if x were 0, 0 squared is 0, plus 1 is 1, log of 1 happens to be 0, okay? So you're, that's interesting. But, so you don't say x has to be greater than 0. This is good for all real numbers. All real numbers. That's interesting. Let me just take a look at that. Yeah. If x were 0, yeah. If x were 0, this would be log of 1. Log of 1 is 0. Derivative of 0 is 0. And sure enough, that would be 0. Yeah. It all works. And works well. Okay? So in the book, I would go up and change that and say u greater than 0, not x greater than 0. Back in that thing that led up to here. All right, let's look at C. Whoa! What in the world does that mean? What have we got here? d by dx of x log x. What in the world is that? Are we dealing with chain rule here? Dorothy? No, we're not in Kansas anymore. What are we dealing with? Product rule. How does that go? First times root of the second, which would be x times 1 over x. What's x times 1 over x? 1. Okay, there's the first part. And then the second part is 1 times the log of x. You got it. Don't tell me they just leave it like that. There's got to be another line here. Oh yeah, there is another line. They just did first times derivative of the second plus second times derivative of the first. The second line here, they take that further, and this is x times 1 over x plus log x times 1, and that would just give you 1 plus log x. Perfect. Okay. Product rule, and then carry it on out. All right. Any questions on that? That was C. Anyone still writing? Okay. Let's go to D. All right. What do we have here? Second? I can't hear you. Okay, 3 times log x, that would be a good start. Times what? And what is the root of log x? 1 over x. Okay? Yep, they just did the derivative of log x. Chain rule. Okay? And that would be 3 times log x times 1. 3 times log x squared. I'm sorry. I almost let you drill me into that one. 3 times this squared. Drop that by 1. Power rule. And then times the root of this. That's 1 over x. So I would write that 3 over x times log x squared. Oh, they didn't change it. Goodness, I would have. That's fine. You can leave it like that if you wish. It just seems a little bizarre. Okay? But that's a perfectly good answer, too. I would have just put 3 over x times the log squared. Log of x squared. Be sure you say, put that in parentheses correctly. All right. Now, before we move on to this, we've got example 14 and 15 to do, but also on the page with 14 and 15, you have a little blurb on John Napier. Why would they bring him up now? He's the guy who developed logarithms, okay? They say invented them. I don't know if he invented them. I guess he came up with the process of them. Scottish mathematician. Also, interestingly enough, he was a pastor. Okay, John Napier. Although he did not introduce the natural logarithm, he used it's sometimes called the Napierian logarithm. He did what they call common logs, which are base 10, not base e. But the main reason he did it was to simplify calculations involving products, quotients, and powers, especially of pretty large-sized numbers. Of course, given the availability of calculators these days, there's now little need for that particular application. However, the value in using logarithmic properties to simplify differentiation will come into play, and that's what we'll do next. Okay, that's example 14 and 15. Now, this is ancient history, but before they had calculators, do you know what we had? People had? Slide rules. Yeah. Any of you even seen a slide rule? Okay, good. Congratulations. Would you have a clue of how to use a slide rule? Okay. What a slide rule did was exactly why Napier did the things. Because if you were multiplying, dividing, taking roots, squaring, anything like this, a slide rule had a rule on the bottom and on the top connected, and then they had a rule in the middle that slid. That's what they call a slide rule. So if you're taking a number, any number, as your base, find that on the bottom, and by all the scales on this are log scales, okay? So they weren't 1, 2, 3, 4, 5 like this. It would be 1, 2, 3, 4. It would be a log scale. If you've ever done any log plotting, say again. What's that?
You have like little beads on the money.
I can't hear
On
you.
the slide rule, you have like some little beads on it.
Okay, I can't hear what you said. I heard on the slide rule, isn't it like something?
Some beads or something on it. You do to the side.
Yeah, they're all numbers, but the numbers are all in log scales, okay? So you find your first number on the bottom and slide the slide over till the 0 lines up there. If you're multiplying the numbers, then find the next number on the slid scale, find it, then take your little window with a vertical line, slide it over there, and read on the bottom scale what your answer is, that you take the anti-log of it, and people just got used to doing that almost in their head, and it was a quick way to do it. You could only get maybe 1 to 2 significant digits, okay? You couldn't get a lot, but I remember when I went off to college. It was my sophomore year of college. Was the first time I saw a calculator. I had heard about it, but I'd never seen one until then. I was in a physics class, big lecture room. Kyle knows the famous university I was going to. Okay, big lecture room, probably held 200 or so students, probably close to that, 100 to 200 students were in there, a physics class, and in walked 2 guys with these strapped to the belt, okay? They're calculators. The rest of us gave out a collective groan and thought, there goes the curve. Because they could get precise answers to as many digits as they wanted to, we could only estimate. They didn't knock us off for estimating. If you got anywhere close, you were okay. But they could do it much easier and faster than having to go. By the way, we swore our slide rules on the belt too, They hung down like a sword, or a little sword. However, it was all nerdy, very nerdy. Okay. But that was my first. Now, Of course, those calculators, a couple things about them. Number one, you had to plug them into a wall, into an outlet. They didn't run on solar or anything else. They didn't have good battery life, if they had batteries at all. So you had to plug them in. So they had to sit somewhere near a plug. So they had that to worry with. We didn't have to worry with that slide wheels like that. Number two, they would add, subtract, multiply, and divide. Not like the calculators you have. And the other fact, they cost about $600. That's why I didn't have a calculator. I couldn't afford a calculator. The slide rule was expensive enough. It was probably $50, $60, unless you could get it used or something. So they were, they were precise devices, okay? And you took really good care of them. But they were nothing like the cost of a calculator that could do basically what the freebies will do today. And and by the way, these were big, bulky things, thick, and just miserable type. But the calculator, the slide rule is based on Napier's logarithm, not Napierian logarithms. Those are the natural. So, too much of that. That was nostalgia time. Okay. Here is what it says. Differentiate this. F of x is equal to the natural log of the square root of x plus 1. Okay? Now, you can do that just with the tools that we have at our disposal right now. Okay? How would you do it? What you're looking for is f prime of x. I didn't say it would be pretty, but you can do it. Okay, you want to rewrite that? Is that what you're saying? Yeah, the log of x plus 1 to the 1/2 power. Very good. Now, if you're really clever, and I know all of you are, and you remember your rules of logarithm, do you remember those rules of logarithm? If you have an exponent inside a log, you can take the exponent outside. So you could rewrite this again to be 1/2 the log of x plus 1. Okay? Now, I think even I can take the derivative of that. What would that be? Anybody? Second? Take the derivative of that. Yeah. 1/2. Second? 1 over x plus 1. Which you could write as 1 over 2 times x plus 1. Which you could write as 1 over 2x plus 2. However you want to write it. Okay? They left it in this form right here. Okay? So by all means, simplify as much as you can. Okay? Now, that's one way using rules of logarithm make differentiation oftentimes much easier. Selective cases. Okay? Everybody got that one? Okay. Let's do 15. F of x is equal to the log of x times x squared plus 1 squared over the square root of 2x cubed minus 1. What we want to do is f prime. Now, certainly you could, just using the derivative of logs and the quotient rule with the chain rule 2 or 3 times and power rules and other things, you could do it brute force, or you could use the properties of logarithm to simplify that sum. Does anyone remember some of the other principles of logarithm? Okay. In case you don't, I was trying to see if they're listed somewhere in your text. I'm almost certain they are, but I just don't know where. I would think in a appendix somewhere, but I'm not seeing it real quickly, so I'll just go over it with you.
That'd be log of u prime minus log of u.
Okay. Now, yeah, that's why I said you could do it that way. That would be brute force. But you can use the properties of logarithms to simplify matters big time. And here are some of those properties. The log of a product is the sum of the logs. A log of a quotient is the difference of logs. Okay? And the log of a power is the power multiplied by the log, like we did in the last one. Okay? So here's what you could do. This would be log of x plus the log of x squared plus 1 squared minus the log of the square root of 2x cubed minus 1. Do you buy that? Properties of logarithm. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. But don't stop there, okay? Let's rewrite this last one to be minus the log of what? Two x cubed minus 1 to the 1/2 power. Okay? So I'm not going to use that one anymore. I'm going to use that one. So let's further use our properties of logarithm. This will be log x. Not going to simplify that any, but we can simplify the next one because that has an exponent. What would that be? What did we do last time? Forgotten it already, huh? 2 times the log of x squared plus 1, okay? Minus, and now we can do that same property again. What would that be? 1/2 the log of 2x cubed minus 1. Are there any other rules for logarithms we can use on those? No. Okay? Now, I don't know if you'll find this helpful or totally confusing, but here's how I remember things. Okay? I think of my arithmetic operations as being in layers. The simplest layer is addition and subtraction. Okay? The layer above that is multiplication and division. And the layer above that is roots and radicals. Okay? And what a log does for you, it takes anything in an upper layer and takes it down to the lower layer. So the multiplication here on the second layer, the log of a product, is the sum of the logs. Okay? Takes it down and makes it an addition. Okay? And the log of an exponent up here takes it down to a product of 2 times the log of that. Now, don't be tempted, or if you are tempted to try to come up with a log for a sum or a difference, resist temptation, because there aren't any. Once you're at that lowest level, a log will not take you any lower. So it can only simplify multiplication and division, exponents and radicals. Okay? Got it? I don't know if that's helpful or not, but that's how I try to help remember. Okay? So if that's now your new function, this is your f of x, you tell me what f prime will be. What's the root of log x? 1 over x. Next. Next. Plus 2 over, second, x squared plus 1. You got something else to do with that one though, don't you?
2 is 2x.
Times 2x. Chain rule. Good deal. Next. Next. Minus 1/2.
6x squared.
1 over. Oh, you said 6x squared, you said, right? That's what you said, right? I thought you did. Okay. 6x squared. It's all right to do it in that order. The order doesn't matter. Just be sure, 6x squared. Okay. But don't forget the next part. Over. I already did it for you. Help me. 2x cubed minus 1. Okay. You have some simplifications you can do, so let's do those. 1 over x plus, and 2 times 2 is 4x over x squared plus 1. Boy, JJ came right in and hadn't even been paying attention. He knew what 2 times 2 was. That was good. I'm impressed. Okay. Next. What can you do to simplify the next one? Yeah, 2 will go into 6 3 times. That's what you were saying, right? Okay, I thought so. Minus 3x squared. I didn't mean to wipe out my x squared. Over 2x cubed minus 1. Okay. That's how I would leave the answer. That would be my f prime. I guess if you were really a glutton for punishment, you would say, oh, well, let's get it over the least common denominator. No, that's not. Okay. I would definitely say not. Let's see what they did. They left it as 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1. Perfect. Okay. Now, something that I was tempted to say before, but I thought it might be too confusing, now they get around to saying, and I think that's going to be on the next slide, so I'm going to go there. Y'all still getting this one down? Oh, and by the way, for those who wanted to, you could have done u prime over u, if you had wanted to, and then simplified, and somehow maybe you could have gotten to this. This is so much easier using properties of logarithms. Do it this way. U prime, I don't even want to think about it. It's a product, the power, a radical, a quotient. That's just to get the u prime, and then over u, that whole mess would be in your denominator. I don't even want to think about it. Okay, good deal. All right. Everybody got this now? I was just killing time while you were finishing. Okay. All right, to erase? Move on? Okay. All right, because the natural logarithm is undefined for negative numbers, it's also undefined for 0, by the way, you will often encounter the expression of the form log of absolute value of u. If you don't know what u is, or u are, however you want to say it, then put it in absolute value bars. Or even if it's a variable x, put it in absolute value bars. Unless you know ahead of time it's u is greater than 0, or x is greater than 0. So theorem 314 states, that's one coming up here, that you can differentiate functions of the form y is equal to log u as though the absolute value notation was not even there. Okay? So here is your theorem that justifies that. If u is a differentiable function of x such that u is not equal to 0. Remember I said, yeah, you can't take the log of a negative number, but you also can't take the log of 0, so u can't be 0. This time they said it right. They said u, not x. Then, d by dx of log absolute value of u is u prime over u. Well, wait a minute. You didn't fiddle at all with the absolute value bars here. You don't have to, because if u is negative, then you would do the negative of that, and that would make it positive. Your derivative would be negative, yeah. So they wipe themselves out. So taking a derivative of a log of absolute value bars, just leave off the absolute value bars and do it the same way you did before, u prime over u. Okay? Now, they do a little proof at the bottom, and that works fine. And you'll see you wind up with a minus over a minus, which again gives you u prime over u. All right. They didn't give you any examples with those. They move right into bases other than e. Okay? Because natural log, the base is always e. Other logs, you could have other bases. The base of the natural exponential function is e. That's that irrational number e. This natural base can be used to assign a meaning to a general base a. Okay? And here's the definition of an exponential function to base a. If a is a positive real number, they don't let a be negative, they don't let it be 0, and neither do they let it be 1. Now that's a little unusual, but there's a reason for it. And x is any real number. X can be any real number. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Then the exponential function to the base a is denoted by a to the x. Whereas before we said e to the x when you're using the natural base, e. But this is a to the x. And is defined as a to the x is the same as e to the log a of x. Okay? Now, you might say, now wait a minute. How did they get that? I don't know if there's time to do that. Let's sort of give it a shot. If you're looking for a to the x, okay, and what you can do is take the log of this, let's call this y, okay? A to the x is equal to y. Take the log of both sides of that. That would give you log y is equal to log of a to the x. But from what we just did, we know this is going to be x times the log of a. Now remember, a is always positive, that's why it is, and not 0, okay? And neither is it 1, okay? So, that gives you log y. How do you undo a log? You e it, right? e to the log y is y, well, that means that's e to the log x log a, okay? And that would be y, because e to the log y is y. So that gives us, and they just rearrange the order, y, which is a to the x, is e, and they put that log a first, log a x, okay? So that's how they get that. It's pretty straightforward, just use of your inverse functions and things like this. Now, if a is equal to 1, here they said it can't be 1. If a is equal to 1, then y is equal to 1 to the x, which is always 1, and that's just a constant function. So why mess with it? I mean, if a was 1, just stop and say y is equal to 1. Constant function 1. Never changes. But if a is positive between 0 and 1, then this is going to result in a negative value if it's greater than, well, a value less than 1. And if it's anything, a is anything greater than 1, then y is equal to 0. So we'll worry with that later. Okay. Now, logarithmic functions, okay, to bases other than e can be defined in much the same way as exponential functions to other bases, as exponential functions to other bases are defined. I guess that sentence makes sense. It's not really clear what they're getting at, but I think I know what they're meaning. So here's the definition of a logarithm function to base a. If a is a positive integer not equal to 1, we've had that before, now x is any positive real number. We're not letting it be negative or 0, okay? But it can be a real number. Fraction, decimal, rational, irrational, it doesn't matter as long as it's greater than 0. Then the logarithmic function to base a, as long as a is not is positive and not 1, is denoted by log base a of x. Again, x can't be negative or 0. Okay? And is defined as log base a of x is, this is written in common log form, log base a, and then to define that in terms of our natural log, it's 1 over log a times log x. Now, that may not be entirely clear right now, but it is indeed true. Here's how I remember it. Since a is subscripted here, that means the base that you're dealing with, put the ln a in the denominator below, and then put ln x in the numerator. I would have written this ln x for ln a, and that to me is easier to remember than this, but it's the same thing. Okay, so I would have said this is log x over log a. Okay, and you see now why a can't be 1. Another reason, because log of 1 is 0, and you can't divide by 0. So there's yet another reason. So again, when you have log base a of x, put the ln x on top and the ln a on the bottom. You got it. Okay. They don't proceed to show why that's true. It's really approached a lot same way the last one was, but I'm not going to take the time to do it. So, all right, to move on. To differentiate or both exponential and logarithmic functions to other bases, you have two options. Use the definitions of a to the x and log a to the x, and this gets you to exponentials, that gets you to natural logs, okay? And differentiate using the rules for natural, exponential, logarithmic functions. Or use the differentiation rules for bases other than e given in this theorem. Now, frankly, I think most of the time I like this better. But here are the others. And they give you the same answers, by the way. Okay? If a is a positive real number, not 1, let u be a differentiable function of x, then d by dx of a to the x is log a times a to the x. Okay? Now, let me remind you where that came from. Let's go back a few slides. This one. Okay? A to the x is e to the log a times x. The ln, natural log of a, times x. Okay? And if you took the derivative of that, you get e to the natural log a of x times log a, and e to the natural log of a, like I said, times log a. Well, this would be a to the x times log a. That is exactly what you would get. And that's what you got. Log a times a to the x. Number 2, if you're differentiating a to the u, then it's again log a in front, and then a to the u, just like here. D by dx of log x is log a times a to the x. This would be log a times a to the u, and then you just chain rule it and do the u dx. Okay? Now, going the other way, taking d by dx of log base a of x, they just say this is 1 over log a times x. I'll show you where that comes from in a minute. And then this is just the same thing. It's exactly the same, only put a u down here because it's a u here, and then do a chain rule here. But if you remember, this right here, like I say, I like this first one better. This would be d by dx. This log base a of x was log x over log a. That's natural log of x over natural log of a. Natural log of a is a constant, right? Not 0, because a can't be 1. So this would be 1 over natural log of a times d by dx of log x is 1 over x. So that gives you 1 over log a times x. Okay? So I don't memorize formulas well. I hate memorizing. So I just remember that and take my derivatives that way. It's easier to me than memorizing the formula. If you're a good memorizer, yeah, do the formulas. I guess I memorized this one, but I developed a little mnemonic device for it. I'm not going to develop one for every one of these, okay? I'm out of mnemonic devices, okay? So, any questions on that?
So you're always going to use a as the base? Why do you use a?
Well, if you're using a base other than e, just call it a. A lot of times it's going to be 10. And if it's 10, just put 10 in there. If it's 2, if you're doing binary operations or bits and bytes and those kind of thing, that's all base 2. Or hexadecimal, which is base 12, base 16, So if you're doing something else, use the base you're using. But if you don't know what base it is, just put it in, and then whatever number you're using, throw that in there, and it works. It's fine. Here is example 16. Do we have time for it? I don't know what time it's getting to be. Huh?
5 minutes.
It's what?
5 minutes.
5 minutes. Oh, good. We can do this. All right. Yeah. I hate when they do this. Okay. Here we're taking the derivative of 2 to the x. Okay? So, what would that give you? D by dx of 2 to the x. Any exponential function, you're going to get itself. So 2 to the x is going to be in there. The only difference is you divide by natural log of 2, or multiply by natural log of 2. Yeah. So it's natural log of 2 times 2 to the x. See, the base is in there. If this had been a e to the x, that would have been natural log of e, which is 1, times e to the x, which is e to the x. Okay. So you just do your log in front, and then that same base. Just like any exponential function, it's going to show up on the right. This just has a coefficient with it, which is the log, natural log of your base. Okay? Now, the next one I'm going to have to pop up in a hurry because I can't see it. Okay. Here's what we're doing. You're doing the y prime of 2. See, they don't give you the function. Y is equal to 2 to the 3x. Okay? So what's going to be your d by dx of that? Natural log of 2 out front, because there's your new base. So there that is. And then what? E, say that again. 2 to the 3x, because that's the thing. And then you got a chain rule, and that would be, someone say it? 3. Perfect. So then, what I think I would do, just like they did, pull the 3 in, put it with the log 2, nothing special, and then your variable out here. Now, I would never recommend doing this, but just as a reminder, this is the same as log of 2 to the 3rd power, remember? 2 to the 3rd power is 8. So you could have written this as log 8, 2 to the 3x. And you say, where did that come from? So that would have been a correct answer. I'm not recommending you do that, but you could have done it just from your rules of logarithms. Okay? That's as simple. I wouldn't do anything more. Okay? They don't even give you the thing. So here's the thing. You take a derivative of log base 10 of cosine x. Okay? D by dx of that. Now these we're taking derivatives of exponents. Now we're taking derivatives of a log. And what would you do with that? Whereas here you multiply by the natural log of the base. Here you divide. So you'd have 1 over natural log of 10. That's going to be there. There it is. Okay? What else? What else? Anything? Yeah, because you're taking a log of it, you put it in the denominator, so it's 1 over cosine x. So there that is. Okay? And what else? Chain rule. Huh? Negative sine x on the top. Perfect. Okay? Now, that would be a perfectly correct and legitimate answer. But they did note that sine over cosine is tangent x. So they pulled the minus out front, the 1 over log 10 as your coefficient, 1 over log 10 as the coefficient, and then tangent x. You have to take that next step, but it's not a bad idea. A lot simpler looking anyway. Okay? Is there a D? Yes, there is. Let's see if we can do D. What's that? Are we out of time? Oh, boo-hiss. Just when we're beginning to have fun. So we'll begin next time with D. Christian said he was always having fun. He's such a brown nose. Okay. All right. All right, homework exercises. Oh my goodness, you were not going to leave without them, were you? Okay, homework exercises. Do any of the odds 5 through 11. They're all at Calc Chat. 5's at Calc View. Any of the odds 13 to 31. They're all at Calc Chat. 13's at Calc View. Any of the odds 33 to 49. They're all at Calc Chat. 35's at Calc View. Any of the odds 51 to 55. They're all at Calc Chat. Any of the odds 57 to 71. They're all at Calc Chat. 57's at Calc View. 73 to 93, they're all at Calc Chat. 73's at Calc View. 95's at Calc Chat. Either 97 or 99 is at Calc Chat. Any of the odds 101 to 107 are at Calc Chat. Any of the odds 109 to 115 are at Calc Chat, with 111 being at Calc View. There's some very famous curves here. 117 is at Calc Chat. 119 should be at Calc Chat. And we'll stop there. We haven't gotten to second derivatives yet. We'll get there. All right, good deal. We'll see you. Wait a minute. What is the day anyway? Wednesday. Have a good weekend, I guess. Okay.